Welcome to Transfer Phenomena Bioprocess Engineering NPTEL course. So, today we will discuss about the fundamental of what are the transfer phenomena here. The movement and transfer tau equal to minus of mu dV by dx. This is called a Newton's law of viscosity, and tau is a shear stress, then the mu is a viscosity, then dV by dx is a velocity gradient. So, what is the velocity gradient here? So, there is a velocity difference v2 minus v1 by x2 minus x1. If you talk about only this one v2 minus v1, we called as a velocity difference, but if you take v2 minus v1 by x2 minus x1, that is called a velocity gradient. So, here the tau is a shear stress. We always, the unit is Newton per meter square, because tau equal to, it look like F by A. So, the force we call Newton, then area is a meter square, Newton per meter square. So, then V is the velocity, the V velocity we used here, that unit is meter per second, then x is the distance is the meter. The finally viscosity mu, that unit is here kg per meter second. We always use the viscosity here kg per. These are basics Newton's law for movement and transfer. So, the Newton's law of viscosity here, the tau equal to minus of dV by dy, what we discussed just now, the tau equal to F by A, that is shear stress, then we call dV by dy shear rate. So, tau equal F by A, and the units already what we discussed, same thing here also we discussed, sometime we define as the dV by dy is the shear rate or velocity gradient. When high shear is there, the possible cell damage, that is a mammalian cells. When it is a low shear, there is a poor mixing, then the most answer is the limitation. So, very simple, if you take like tau equal to minus of mu dV by dy n, if n equal to 1, we always call as the Newtonian fluids. If n equal to less than 1 or n equal to greater than 1, it's all fall in the non-Newtonian fluids. So, here normally the Newtonian fluids are gases, the low molecular weight liquids, we always use this one. Whenever many polymeric liquids like particulate suspensions, like other complex, all is coming under the category of non-Newtonian fluids here. So, what are the type of fluids here? What we discussed, same thing, the example here, the Newtonian fluids is the viscosity is constant, what we discussed, the mu is the constant. That is a water, ethanol, this is all coming here, the best example for. For non-Newtonian fluids, viscosity changes with the shear rate, that all coming in the non-Newtonian fluids. But again, even with respect time also will change, that we discuss the forthcoming classes. So, there is a non-Newtonian fluid example, xanthan gum, then fermentation broth. Like the biological fluids includes like a blood, then cell suspensions, then broth, all coming under the non-Newtonian behaviors. So, the best example for fungal culture in bioreactors and then extracellular polymer production. See, the like polysaccharides results gives a strong non-Newtonian behavior. So, when you talk about this one, one is the famous for Reynolds experiments here, that is very important. Say example, the pipe flow, how the flow pattern is happening here. When your fluid flow through a pipe or channel, how the flow can vary with respect to conditions. So, who carried out the best this one? That is Reynolds in 1983. He only carried out in the circular tube the experiments, the flow of water. So, Reynolds also studied the how the effect of varying condition in the flow in the colored liquid, of the colored liquid. So, for example, the varying velocity. So, here just velocity if you vary, what is happening here. So, that part of also is studied, studied here. When the velocity is very low, the thread colored liquid here remain undisturbed here. So, the water streams moves steadily without mixing. So, move as it is here. So, that condition we called as a viscous flow, or we called as a laminar flow. So, this is a streamline flow. So, if there is no disturbance, it's move as it is, then that flow called as a laminar flow. So, there is a three type of flow is there. The next one is for transitional flow. The same experiments, and but you increase a little bit velocity, then the point is critical velocity. So, it began as a waiver, but there is no mixing occurs, that is called as a transitional flow. But if you increase the velocity to high values, then eddies forming here. So, then the colored liquids mix like completely with the water. So, this type of flow we called as the turbulent flow. So, now three type of flows here. One is a laminar flow, then other one is the turbulent flow, then the transitional flow. So, what are the result of this experiments here? The Reynolds found the condition here. One is the diameter of pipe, then velocity of this one, then density of fluid, then viscosity. So, there is the main play here d, v is the velocity, then density is the rho, then viscosity we call as a mu. So, we always write this is called NRE. NRE is a Reynolds number. So, the Reynolds numbers, the function of only the pipe diameter, velocity, then density, then viscosity of fluids here. So, this Reynolds experiments, how this one, you take one side is water, other side is a dye in water, just pause it, but as it is first dye moves the straight line without mixing, just see here it is moving straight line without mixing. So, we called as the laminar flow, there is no mixing, so we called as a laminar flow. Then suddenly the dye starts little bit oscillate, mixing also slightly, that type of flow we called as the transitional flow, what we discussed here. Then you increase the velocity, so the dye mixes throughout the liquid, so that we called as a turbulent flow, what we discussed just now, turbulent flow. So, here completely mixing here, it just for to example to show you how the Reynolds pattern, the flow pattern occurring in the pipe. So, Reynolds number we always write NRE equal to dV rho by mu. So, d stands here, the diameter, the unit is here meter, then v is the velocity we write for meter per second, then the density here kg per meter cube, then the mu is the viscosity. So, kg per meter a second. So, all will get cancelled here, you just see here meter cube, here also 1 meter is there, then the second get cancelled. Finally, it is a dimensionless numbers, there is no dimension, it is a 0 dimension. There is no dimension, so only numbers here. So, that is why we called as a dimensionless number. If a dimension is there, some units are there, that is called dimension number, but this is a dimensionless numbers. So, for flow through pipe, the circular pipe, the Reynolds number is less than 2000. So, always roll Reynolds number here. But if it crosses above 4000, and this is called a turbulent, and that is called, it is a mixing chaos, then high Reynolds number here, whenever we increase that one. So, intermediate here, that is a transitional flow, that in between 2100 to 4000. So, in between the Reynolds number, this always we called as a transitional flow. So, here one small example, the broth density is available here rho, then velocity is here 0.5 meter per second, then there is a diameter also here, then viscosity is in terms of 0.02 Pascal seconds. So, you just substitute everything, then we can check 2500. So, this 3GN is, it's not in the laminar flow, it's not in the turbulent flow also, it's coming in the intermediate, it's called a transitional flow, because coming in between that one. The simple example for here. So, another example, water at 300 Kelvin, the flowing at a rate of 10. This is a different unit, normally we will use for SI units, but of course we should know how to convert also. In a pipe having the inside diameter of ID 2.067 inch. Calculate the Reynolds number here, but given this one, the density is here given, density is a 0.996 gram per cc, that you can convert as a kg per meter cube. So, there is a viscosity in the centipoise. First you have to convert, this is a flow rate 10, but you have to convert in terms of our own units, SI units. So, all units will be able to solve in SI units, that will be easy to solve. So, flow rate is here, we convert in terms of meter cube per minutes, then again meter cube per second, you convert because minutes, then convert in terms of second. Same way for diameter, the 2.06, this is ID inch here, convert in terms of meter. So, density is there, that is a gram per cc, you convert in terms of kg per meter cube. So, finally, we got all values in terms of SI units. Now, we can solve what is the Reynolds number. Then again centipoise, 0.8007 centipoise, you convert in terms of kg per meter second. So, what is Reynolds number here? Reynolds number here dV rho by mu. The problem here, we got only value of Q, volumetric flow rate. If you make volumetric flow rate divided by cross sectional area, then we get a velocity, because here meter cube per second, then area meter square, then we will get a meter per second velocity. So, volumetric flow rate divided by area, we will get a velocity. So, once velocity, if you done this one, then area already available pi r square. So, from there we can get the velocity. The velocity is the 0.291 meter per seconds. So, you know velocity, you know diameter, we know viscosity, then we get the, we can calculate the value of Reynolds number. We got 19,030. So, it is a crossing above 4,000, then we call it as the turbulent flow. Same way for the problem 2, the whole milk, the 293 Kelvin, the density is 1030 kg per meter cube, the viscosity is 2.12 centipoise, is flowing at the rate of 0.605 kg per second. The previous problem volumetric flow rate, and here is a mass flow rate. Mass flow rate we always write kg per second, volumetric flow rate we write for meter cube per second. In a glass pipe having diameter is 63.5 millimeter. Calculate NRE, calculate the flow rate meter cube per second, meter cube per second, the Reynolds number, but we kept as a 2100, and velocity. So, first anyway diameter we know, you have to convert in terms of SI units, and then density also done, and mu also converted in this one. Then mass flow rate here, but mass flow rate if you want to solve, first you have to get a volumetric flow rate V equal to mass flow rate by density. Mass flow rate by density here, then only we can get a volumetric flow rate. The mass flow rate here kg per second, the density is a kg per meter cube. So, if we cancel it, then we will get a meter cube per second volumetric flow rate. So, finally, we got volumetric flow rate, but still we cannot use this equation, because you have to convert in terms of the volumetric flow rate to velocity. So, that is called velocity, the V is the 0.185 meter per second. So, once you know velocity, you know velocity, you know diameter from previous problem, and then density also you know, viscosity, you get the value of NRE. So, NRE is a 5710, 5710, it's crossing this one, it's fall in the turbulent region. But the same problem they ask, if Reynolds number 2100, so what is the flow rate? So here the 2100, you get the value of first velocity, it's rest everything same. Once velocity done, you want a flow rate, the flow rate Q here, velocity meter per second into, if you multiply area, we will get volumetric flow rate, meter cube per second. Next to the problem 3. So the oil is being pumped inside the 10 millimeter diameter, the diameter is 12 millimeter diameter, the Reynolds number is 2100, the oil density is 855 kg per meter cube, then viscosity is also there. They are asking what is the velocity in pipe. The same equation that reversed here, the Reynolds number equal to dV rho by mu. So velocity equal to Reynolds number into mu by d rho. So there is Reynolds number already available 2100. So all values are just substitute and get the value of velocity. But same thing they are asking, in order to maintain Reynolds number 2100, the same velocity, but only the varying the density of values, viscosity, then what is the diameter. So in the same case, you can take a diameter and substitute all the values and get the value of diameter 6.6 millimeter. So what is the momentum balance here? The Navier-Stokes famous equation. This is a rho of du by dt, then delta p is a del p is a pressure force, then mu del square u is there, then rho g. So there is a gravitational force, this g is a gravitational force here, then this is involves a lot of diffusion, because this term is still diffusion. Maybe the forthcoming class we discuss more on depth of how the absorption through packed bed column, then concentration difference in the packed bed column, everything we will discuss. But this is very fundamental here. Again, what is the rho, mu, everything given here. So, and this is the accumulation term, we call the accumulation. And this is a pressure force, we call the pressure force. And there is a diffusional, there is a diffusional here. Then this another one is the last one is the gravitational here. So what is the flow in bioreactors? It's a agitated bioreactors requires definitely turbulent flow for good mixing. Otherwise, its mixing is very, very complicated here. Then the impeller design and the speed is definitely affect the flow regime. Non-Newtonian fluids complicate the prediction. Whenever the non-Newtonian fluids is not very easy to predict, is very, very difficult to predict that one. What is the shear effect on cells? Normally, the bacteria and yeast are generally the shear tolerant, but the mammalian, the plant cells are very shear sensitive. So what strategy we have to follow here? We have to maintain the low shear impellers, then the bubble free aeration. What is the case study here? Case study is a mammalian culture here. We have to go the high impeller speed. Sorry, if you go the high impeller speed, it get a damaged cell. Then wave bioreactors normally used to for the gentle mixing. Whenever the gentle mixing is there, the wave bioreactor will use here. Then the improved viability and the same way for yield. For scale up, if you want to scale up the challenges, what are the challenges here? Lab scale work very nicely because it's a mixing effectives, but whenever if you go to industrial scale, it makes a lot of dead zone. It's a create a dead zone, then it's very difficult to scale up here. And again, of course, we have to increase the mixing time with the volume. Wherever volume this one, we have to increase the mixing time with the volume. There is a oxygen gradient appear in the large, whenever the fermenters, big large fermenters are there, there is the oxygen gradients are there. That's a difference of oxygen level in a different place, so that the cell growth is very difficult to here. So what is the heat transport? in the Fourier's law, last class we discussed same way, the Q by A equal to minus of K dt by dx is the Fourier's law of heat conduction. So, we write for Q rate of heat transfer, that is a unit here, Q is a joule per second. Then the area we write units here meter square. This is a famous Fourier's law of heat conduction. The K we talked about the thermal conductivity, that unit is watt per meter Kelvin. Then the temperature is a Kelvin because the dt we measure as a Kelvin. The distance here, the x distance is a meter. How much distance this one, that we always write the in terms of meter. So, is the heat transport in the Fourier's law, Q by A equal to minus of K, Y minus sign is always get degrees. The temperature is from drop from higher to lower order. It's a famous heat flux equation. So, here why heat flux here, because here Q by A, the Q here joule, then per second, then area is the meter square, 1 by meter square. So, then we call as the heat flux. Any driving force, the joule is a heat transfer driving force, any driving force with respect to unit area and unit time, we always call as the heat flux. Already same thing when we discussed what is the mass flux and what is the momentum flux also. So, the heat transfer is mainly its exchange of thermal energy through body or between the bodies where there is a temperature difference. So, the heat transfer challenges in the large bioreactor here, there is a high broth viscosity, it is a reduce the convection. If it is a large volume, then the poor temperature uniformity, wherever the hot spots may kill the cells, then lower productivity. So, what are different type of mode of heat transfer here? It starts with the conduction, convection, radiation. Conduction is only solid phase. There is a heat transfer through solids or stationary fluids. It is like one dimensional heat flow. We can even do 2 dimensional, 3 dimensional also. It is always the Fourier's law, the play in the conduction. Wherever convection, the movement of fluids transfer heat, there is a Newton's law of cooling we always use here. There is a 2 type of convection, one is the natural convection, another one is a forced convection. So, natural convection occurs naturally, the forced you have to apply externally some pressure, some pumps, then convection occurs here. The last is the radiation. The radiation does not require any medium for transferring heat from one to other one. So, there is a 2 application of heat transfer, this one is the temperature control, how to control temperature, this one, other one is for the sterilization, the batch sterilization process. So, what are the importance of heat transfer here? So, the fermentation reaction if exothermic, definitely if the microbial metabolism involves the oxidations like substrate like glucose, sucrose, amino acids. If catabolic reactions release the heat, so here it substrates energy captured ATP. Whenever you increase the heat, there is a fermentation process also. So, very difficult to do. So, that is only in the cellular level, the heat is less, but the large scale culture, the cumulative heat is very high, enormous here. Whatever temperature affects enzyme activities, yes, if temperature is more, it definitely affect the enzyme activities. Same way for the growth, even if we get increase 1 to 2 degree, and we will get a different type of byproducts. So, the temperature affects the enzyme activity is a very important here. So, whatever the excess heat, if whenever there, of course, we have to remove, how to remove that one, and we of course you have to use for some exchanger, heat exchanger, to such a way that we can remove this one. So, if temperature rises, what will happen? It reduces the growth rate, unnecessary it goes to some other metabolic pathway, then it will get a stress protein, and finally it gets the productivity gets a reduce. So, what are the solutions? Same, we have to use the cooling jackets around the fermenters, or internal cooling coil we have to use, or sometimes external heat exchanger or agitation we have to use here. So, then the excess heat we can always avoid here. So, the famous heat law, the Q equal to minus Fourier's heat, this one Q equal to minus of K T T by dx, the K here thermal conductivity, this is a temperature gradient. I already discussed what is the temperature difference and temperature gradient. The simple example for problem, there is a 10 centimeter thickness, the thickness x is the thickness, then temperature vary from one to other point, and then again there is the thermal conductive values are there, K value, and area also there. Just directly you get the value of what is the Q, the heat transfer rate, we will get in terms of 13.9 joule per second. So, this is a heat transfer, the Q values. So, neutrons of cooling, there is a two there, one is the convection. So, wherever convection part, we always use Q equal to HA delta T. So, the delta T is the difference of surface here, what is the temperature of surface and the temperature of fluid here. It definitely will useful for the cooling coil and the jackets we will always use. But this is the Newton law of cooling for convection Q equal to HA. But whenever if you want to overall heat transfer coefficient, we have to use Q equal to UA delta T. The U stands here overall heat transfer coefficient, the H stands here individual heat transfer coefficient. Sometimes we have to add the wall the conductivities all together, but the U stands the overall heat transfer coefficient. How we have to account the both conduction convection in series, but here only is the convection part. So, of course, these are all the design parameters. If you want to use a heat exchanger, the fermenter jacket, definitely we need the overall heat transfer conduction convection knowledge. So, here again the penicillin fermentation, if exothermic reaction release large amount of heat, it is really very difficult. Of course, then we have to use the heat exchanger. Same way for the scale up, you want to scale up, it get definitely if it not inadequate cooling, it definitely affect the penicillin fermentation. So, what the key takeaway points here, we discussed now what is the Newtonian, non-Newtonian behavior and the Newton's of viscosity. Then we discussed about the Reynolds number, how the Reynolds number works. Reynolds number here, either it's a laminar flow or turbulent flow or transitional flow, and we just touched the Navier-Stokes equation, how the Navier-Stokes equation, the fluid motion based on the convection momentum. Then finally, these all like a momentum, then heat, then all it will be a, we need thorough knowledge for whenever if you want to do bioreactors to scale up, we need definitely thorough knowledge about momentum, mass, heat transfer, otherwise we cannot set up the large scale reactor here. Thank you.